Welcome dear students, we are on the CEC Gurukul lecture. We are in the series of the electronic circuits. So in the electronic circuits we discuss the many components which are used in development of the electronic gadgets. So when we discuss the many electronic components, so today we will discuss the filters which are also important in the development of the electronic circuits. So filter is a circuit. What is a filter basically? In this lecture we discuss the filter and types of the filter, its application, its advantages, its disadvantages we will discuss in this lecture. So first we should know that what is the filter. So filter is basically a circuit capable of passing or amplifying certain frequencies while attenuating other frequency. It means the filter can extract important frequency from the signals that are also contain undesirable or irrelevant frequency. Sometimes we use the relevant frequency also, sometimes it can stop the irrelevant frequency. So filter is a circuit capable of passing or amplifying the certain frequency while attenuating other frequency. So filter can extract the important frequency from the signal. So in the field of electronics there are many practical applications of the filter. First we discuss that what are the application, why we are discussing this topic, where we can use these filters. So radio communication use this type of the filter. So filters enable radio receivers to only see the desired signal while rejecting all other signals. So a particular frequency signal we can get through this radio communication through by using this radio filters. So assuming that the other signals have the different frequency contents and that is not required, so it will be filtered out through these filters. Another important application of this filter in the DC power supplies. It filters, these filters are used to eliminate undesirable high frequencies like noise that are present on the AC input line. So a noise can be filtered through these using this filter. Additionally, filters are used on a power supply's output to reduce ripples also. Another application of this filter is audio electronics. In the audio electronics we use the filters. A crossover network is a network of the filter used to channel the low frequency audio to the woofers, mid-range frequency to the mid-range speakers and the high frequency sounds to the tweeters. So in the audio electronics these filters are most commonly used to get the variation in the frequency of the sound in the audio and to get the audio signal output. Next important is the analog to the digital conversion. Through this filter the analog to digital conversion are possible. Filters are placed in front of the ADC input to minimizing the aliasing. So these filters are used to get the desired output. So what are the four major types of the filter? As you see on the screen that we are having the four major type of the filters. First filter is which include the low pass filter, second is the high pass filter, and third is the band pass filter, and last one is the notch filter, that is the band rejected or the band stop filter. So take the note however that the term low and high do not refer to any absolute value of the frequency, but rather they are relative values with respect to the cutoff frequencies. So using this, what now we discuss one by one. What is the low pass filter? That passes the low frequency signals but reject the high frequency. As the name suggests, low pass means it will pass the low signals. It means it passes the low frequency signals but rejects the high frequency. A high pass filter does not does just a opposite, like it will pass the high frequency and blocks the low frequency. Band pass filter will only pass the frequency within a certain range, a band. Band means a certain range. So, band pass filter will only pass the frequency within a certain range. And finally, the notch filter will reject the frequencies within a specific range. It will reject, it will pass, band pass will pass the signals of a particular frequency, and the notch filter will reject the frequency within a specific range and pass all the frequency outside of that range. So, frequency is measured in cycles by seconds or the hertz. As we know that we can measure the frequency in the cycle per second or in the hertz. So, for example, human hearing reaches up to the around 10 to 20 kilohertz. So, 10 to 20,000 times per second we can get this measurement. So, a Bluetooth or a Wi-Fi radio signal nowadays we are using daily at other extreme oscillates at the frequency 2.4 gigahertz. We are in the 5G generation. So, we use 2.4 gigahertz and that is the 2.4 million times per second. You see on the screen there the various pass filter, low pass filter, high pass filter, band pass filter and notch filter. You see on the left hand side the signal is going here and the output you will see in the different way, right. This is the output. So, we discuss one by one what is a low pass RC filter. We take the one of the example by using the RC, resistance capacitor circuit. So, what is the low RC filter? This simplest low pass filter is made using only the resistors and the capacitors and is appropriately called it as the RC filter. You see right hand side we are using the resistor and a capacitor that is defined by R1 and capacitor defined by the C1, and battery is attached with and one point is connected with the ground. So, in this circuit the signal goes into the R1 resistors and the filtered out is taken off the node between the R1 and C1. So, capacitor passes high frequencies and blocks low frequencies. So, the low pass RC filter, low frequency will see C1 as very high impedance open circuit and the high frequency will see the capacitor as low impedance to the ground. So, in the low pass RC filter all the high frequency go through the C1 to the ground and we can get only the low frequency, and this essentially removes the high frequency components, and whereas the low frequencies are passed on the output. So, the cutoff frequency is the frequency at which the filter begins filtering. So, this is the one of the important term, that is the cutoff frequency, that is the frequency at which the filter begins to filter. So, for a low pass filter, frequency below the cutoff frequency are passed and those above the cutoff frequency are not passed, they will be rejected. So, this is the in this case this is the low pass filter, as the frequency below the cutoff frequency will pass and the other will be rejected. So, no filter is perfect true and there will be the some frequency around the cutoff frequency that are passed to the output highly attenuated or the reduced. So, the equation to calculate the cutoff frequency for an RC filter you see on the screen is defined as f is equal to 1 by 2 pi RC. That will be what sets the cutoff frequency is essentially R times the C. The factor R is commonly called the time constant of the filter. So, this is the f is equal to 1 by 2 pi RC. So, next type of filter is the high pass RC filter, just opposite to the to the low pass filter. So, in this mechanism what we do, for a high pass RC filter we simply swap the resistor and the capacitor. We can swap the placement of the resistors and the capacitors. The capacitor is still a high impedance to the low frequency and a low impedance to the high frequency. So, but by swapping the two components, the low frequency are now blocked by the capacitor, and it means they will not pass the signal through the C1 to the output. They do not pass through C1 to the output, whereas the high frequency is allowed to pass through this output. You see on the screen, then you just see the upper side. In the previous diagram we see that on the upper side we are having a resistors and the capacitor on the right hand side, but here you see we just change the position, that is the C1, and on the upper side, now the right hand side we have R1. It means the high signal will be passed and the low signal will be blocked. So, cutoff frequency follows the exact same equation as at the low pass RC, and except that now the frequency above this cutoff frequency are passed, and hence the name is, that is the high pass filter. The low pass filter, LC filter. The next step up for the RC filter or the LC filter, where the resistor is replaced with the inductors. That is why it is a LC. An inductor functions just the opposite from the capacitor. So, an inductor passes the low frequencies and blocks the high frequencies. So, for the RC filter, the resistor simply sets the cutoff frequency. If there is no resistors, the cutoff frequency becomes infinite, meaning every frequency is passed and no filters at all occurs. So, we use the R here. You see here, for a simple RC filter, there it's only the impedance of the capacitor that changes with the frequency and the performs the filtering. You see, in place of the R1, here we put the L1 impedance are put. Next, on the other hand, with the LC filter, both the components contribute to the filtering. Like for the low pass LC filter, in addition to the capacitor sending the high frequency to the ground, high frequencies are also blocked by the inductors from reaching the output. So, both will work. The capacitor will send the high frequency to the ground, and the impedance, and that will inductor will block the high frequency to reaching the output. So, for the low frequency, L1 looks like a short and the C1s like an open circuit, therefore passing those frequency on the output unattended. So, for high frequency, the L1 looks like an open and C1 looks like a short to ground. So, therefore, no high frequencies will pass along the output. Then the equation for the cutoff frequency of the LC filter is similar to the IC filter, except instead of simply R into C, the factor becomes the square root of the L into C. You see on the screen that F is equal to 1 by R into pi square root of L into C. Now, see, high pass LC filter, that was a low pass, and high pass just opposite, just as we did for the high pass RC filter. For the high pass LC filter, we simply swap the positions of the inductor and the capacitor. Now, the capacitor blocks the low frequency and passes the high frequency, while the inductor sends the low frequency to the ground. Therefore, on the frequency above the cutoff frequency will pass on the output. So, you on the screen, just we change the position, and this is the LC high pass filter. Now, filters are divided into two types. We can say that the filter are placed in the two categories. One is the passive filter, second is the active filters. The passive filters include only the passive components. What are the passive components? There are resistors, capacitor and the inductors. In contrast, active filters use active components such as op amp, in additional to the resistors and the capacitor, but not the inductors used in the active fast filters. So passive fast filters are most responsive to the frequency range from 100 Hz to the 300 megahertz. So passive fast filter can pass this type of frequency, but the limitation on the lower end is the result of the fact that the low frequencies, the inductance or the capacitance would have to be quite large. So upper frequency limits is due to the effect of the for the capacitance and the inductance. So careful design practices can extend the use of the passive circuits well into the gigahertz range. So in other words, the active filters are capable of dealing with the very low frequency approaching to the 0 hertz. For the high frequency we use the passive filter, but for the low frequency we use the active filters, and they can provide the voltage gain that will not be possible in the passive filters. So an active filter can be used to design high order filters without the use of the inductors, and this is important because inductors are problematic in the context of the integrated circuits manufacturing techniques. Active filters are less suitable for very high frequency applications because of the amplified bandwidth limitations. So radio frequency circuits must often utilizes the passive filters. So what are the key points and the terms where we use in the filters? So response curve are used to describe how the filter behaves. As we see in the previous diagram, on the right hand side we have the various curves. These various curves define the behavior of the filters. A response curve is simply a graph showing an attenuation ratio, that will be the V output divided by V input, voltage output divided by the voltage input versus the frequency, and attenuation is commonly expressed in the unit of decibels, that is the dB, and the frequency can be expressed in the two forms, either the angular form, that is omega, and its unit is radian per second, or the more common form of the f, as we always use in the laboratory. When we measure the frequency we use the f, and unit of hertz, that is the cycle per second, that is a hertz f, and that is the cycle per second, and these two forms a relation omega is equal to 2 pi f. So you see on the screen that this is the final output that we can get, the graph between the frequency versus the output. So final filter responses curves may be plotted in a linear or log linear or the log form. You see, these are the low pass filter output, this is a high pass filter output, this is the band pass, and this is the notch output, all having the different form. And the most common approaches is to have the decibels on the y-axis and logarithmic frequency on the x-axis, and we can get this type of output. And next is the technical terms that are commonly used when describing the filter responses curve is the 3 dB frequency, minus 3 dB frequency, and that is written as f3 dB. This term is pronounced as minus 3 dB frequency and corresponds to the input frequency that causes the output signal to drop by 3 decibel relative to the input signal. It means this signal we require in the form of the output 3 decibel signal. The 3 decibel signal is also referred to in cutoff frequency. It means up to now we are getting the output and above it we will not get it, and it is a frequency at which the output power is reduced by 1 or a half, which is why this frequency is also called the half power frequency. And this is frequency at which the output voltage is the input voltage multiplied by 1 by root of 2. For the low pass and the high pass filter, there is only the 1 minus 3 decibel frequency. However, there are the 2-3 decibel frequencies for the band pass and the notch filters. These are normally referred to as the F1 and F2. Next important parameter is the central frequency, that is defined by the F0 or F0. The central frequency, a term used for the band pass and the notch filters, and this central frequency that lies between the upper and the lower cutoff frequencies, and the center frequency is commonly defined as either the arithmetic mean, see the equation, and geometric mean, or the lower cutoff frequency and the upper cutoff frequency. Next important term is the bandwidth, and we commonly, when we discuss this in terms, that is the bandwidth. The bandwidth is the width of the band pass. We generally call the what is the bandwidth of the signal. So what is this bandwidth? Bandwidth, which is denoted by the beta, and the bandwidth is the width of the pass band, and the pass band is the band of the frequency that do not experience the significant attenuation when moving from the input of the filter to the output filter. So next is the stop band frequency. Next parameter is the stop band frequency, that is defined by the Fs. This is the particularly frequency at which the attenuation reaches a specified value. So for the low pass and the high pass filter, frequency beyond the stop band frequency are referred as a stop band frequency. For the band pass and the notch filters, two stop band frequency exist. The frequency between these two stop band frequencies are referred to as the stop bands. Thank you very much.